Okay, we have a question from Chapter 10, Section 2, number 39. Financial planning. Mark has $100,000 to invest. His financial consultant advises him to diversify his investment into three types of bonds: short term, medium term, and long term. The short term bonds pay 4%, intermediate term bonds pay 5%, and long term bonds pay 6%. Simple interest per year. Mark wishes to realize a total annual income of 5.1%, with equal amounts invested in short and intermediate bonds. How much should he invest in each type of bond? Okay, so let's see. We need to come up with sort of true statements from all of this. So we got, I don't know, should I use short term, I term, and L term? I don't know if S, I, and L will be the best variables, I guess. But let's just say X, Y, and Z. Fine. So let X be let X equal amount. Come on. Oh, it's gonna be one of those days. Amount invested in short term. The short-term bonds. We're going to let Y equal the amount invested in the intermediate term. And let's let Z equal the amount invested in what's long term bonds. Okay, so short term might be something like 6-month bonds. Immediate might be something like a 3-year bond, a 5-year bond, and long-term bonds might be more like a 10-year bond, right? A bond is a loan. You're lending somebody money and they're paying you interest for letting them borrow the money. If you let a company borrow your money, like say Google, hey Google, here's my money, pay me interest, that's called a corporate bond. If you let a local city borrow your money, maybe they want to construct a new school or something, that's called a municipal bond. If you let the federal government borrow your money, then they call those treasury bills. So either way, in exchange for letting them borrow your money, you get some sort of return on that. In reality, it's a little bit more complicated than this, but we're just simplifying it to be a specific percentage, returned, and we're also completely ignoring the danger that if you let somebody borrow your money, they might not pay you back, right? So there's always a little bit of danger for that. The bigger the danger, then the higher the return, right? If you lend your money out to a really, really stable company, then you would expect a low interest rate because it's a really, really good, safe investment. If you lend your money to a company that's kind of high risk, there's a fairly reasonable chance they may not be able to pay you back your money. Then you would expect a really high interest rate return, right? So the more risk, the more reward. Likewise, the length of the bond also affects the interest rate. Usually, the short term would give you less of a return, and the longer the commitment to borrow, right? If you're committing to letting somebody borrow your money on a for 10 years, a longer commitment, you would expect that return to be bigger, right? Because you're letting them borrow it for a longer period of time. There's more flexibility for them to invest in the long term and find a way to do something with your money and therefore reward you with a higher interest rate. That's not always the case. In some very rare cases, the short term ends up being higher than the long term. They call that an inverted yield curve. When we're talking about federal bonds, that's an interesting phenomenon because in the past, whenever we've seen that happen, that the short-term bonds are actually paying out more than the long-term bonds, we call that an inverted yield curve. And it's usually an indicator that something really terrible is about to happen to the economy. It has been, like when we go back into history and we notice when these things have happened, usually shortly after there's some massive recession or something unhappy in the economy. So that's not good, and it's been a pretty good predictor in the past, and we've seen that happen very recently as well. The short term and the long term inverted within the last year or so. So not a good indicator. This was even before COVID. Last year, I think the yield curves inverted. Anyway, back to this. So define your variables. The variables are the amount, right? It's an amount of money. And we need to come up with statements that are true based on the information that we have. So one of the simple statements that we can come up with is that all of these amounts must add up to the total investment of 100,000, right? So, equation number one, I got to come up with three equations, right? How do I know three equations? Because there's three unknowns. Three equations, three unknowns. Equation number one, I'm going to say that x plus y plus z must be equal to 100,000. Okay, that makes sense, right? Mark has a total of $100,000 to invest, so the sum of all three of these must be equal to 100,000. Also, they gave you a little thing down here. Mark wishes to realize a total income of 5.1%, so that's important, with equal amounts invested in short-term and long-term bonds. So the short-term and the long-term have to be equal amounts invested. So it must mean that whatever we invest into the short term is equal to the amount we invest in the long term. Right? That's this part. Equal amounts invested in short term and with equal amounts invested in short and intermediate, not short and long. Short and intermediate means that the amount invested into the x must be equal to the amount invested into the y. Right? Good. Okay, and then just to put it in this format where all the letters are on the same side, all the variables are on the same side of the equal sign, I'm just going to rewrite this as x minus y equals 0, and I'm going to call that equation number 2. Good. And then equation number 3 is going to be a little bit more involved. It involves all these percentages everywhere, right? So the key is that we want to realize a 5.1% annual interest rate, simple interest rate, right? So it's simple interest rate. It means that I want my total return to be equal to 5.1% of the 100,000. So 0.051 times 100,000 will represent the total return that I want, right? And how do I get that? I'm going to get that from three separate investments. It's going to come from the amount of return that I get from the short term, in the short-term bond, which is going to pay off at 0.04 times x. This will represent how much money I get from that investment, right? The amount invested times the percentage rate times 1, which is 1 year, right? We're doing simple interest. Plus and then 0.05 times the intermediate term plus 0.06 times the long term. Good. Questions? No? Okay, so then to simplify that a little bit, we get that 0.04x plus 0.05y plus 0.06z must be equal to $5,100. 5.1% of 100,000 is $5,100. Good. So I can use this as my equation number 3, but I might as well just simplify it a little bit, because if I move the decimal over 2 spaces or multiply everything by 100, multiply this by 100, multiply this by 100, then I really just get to move the decimal over 2 spaces, 1, 2. Then I'll get a simpler statement that 4x plus 5y plus 6z is equal to 5100 with 2 extra zeros added on, which turns it into 510,000. And then I'll use that as my equation number 3. Good. Okay, so from all of that, we get that we have the following system of equations. We have x plus y plus z equals 100,000. We have that x minus y equals 0. And we have that 4x plus 5y plus 6z equals 510,000. Right? So there's my system of equations I need to solve. So lots of ways to solve this. If I do the substitution method, that could be a really easy thing to do for this one. I can solve for either x or y and then plug it into here. So if I solve for x equals to y, for example, I could end up with y plus z. So I end up with an equation that only has y's and z's. And then I can do the same thing over here and again end up with a brand new equation that only has y's and z's. Good. Or I can take equation number 1 and equation number 3, cancel out the z, and then I would end up with a brand new equation that only has x's and y's, and coupled with this one, I would have 2 equations to solve for the x and the y. So I'm going to choose to do that instead. Equation number 1, equation number 2, and equation number 3. Okay, so I'm going to take equation number 1, x plus y plus z equals to 100,000. And I'm going to take equation number 3, which is 4x plus 5y plus 6z equals to 510,000. Right? And my goal is to eliminate the z. Eliminate the z so that I have a brand new equation that only has x and y, and then I can come back and play with equation number 2, and then I'll be able to have 2 equations with 2 unknowns. Okay, so to solve for this one, focusing on canceling the z, all I'm going to do is multiply equation number 1 by a negative 6. Good. By a negative 6. So then I'll end up with negative 6x minus 6y minus 6z minus 600,000. And then equation number 3, I'm not going to do anything to it. equation number 3, I'm just going to copy it over. We have 4x plus 5y plus 6z equals to 510,000. Good. So now I'm ready to add these. Right, and then great, those cancel. I'll end up with negative 2x minus 2x minus y equals to negative 90,000. Good. And that's what we'll consider my new equation number 4. Good. So I'm going to take equation number 4 and couple it with equation number 2 from before. Right, so let's go back and get sort of the big picture. Come on. So equation number 2 is here. I'm going to combine that one with equation number 4. Let's go down here. And so I'll get x minus y equals 0, and minus 2x minus y equals negative 90,000. Right, and so this is equation number 4 and equation number 2, the original one. And these are almost ready. I can cancel out the y fairly easily, right? All I have to do is multiply equation number 2 by negative 1. Multiply it by negative 1. And then that'll give me a minus x plus y equals 0. And then for equation number 4, I can just copy it over, same thing. Equation number 4, no change. You get a minus 2x minus y equals minus 90,000. Good. Now we add them. The y's cancel, and I end up with minus 3x equals to minus 90,000. Dividing them, we get that x equals to negative 90,000 divided by negative 3, so x equals to positive 30,000. Good. And then that's going to unravel everything because we have that x minus y equals to 0. So clearly x equals to y. Let's go over here. Okay, so we have this one. And that's 3. Okay, x equals to 30,000. So now from equation number 2, we had that x minus y equals to 0. So 30,000 minus y equals 0. So y also equals to 30,000. As one of the conditions or restrictions indicated that x must be equal to y. Right? The amount invested into the short term and the intermediate term were the same. And now we can just use equation number 1. Equation number 1 indicated that x plus y plus z have to be equal to 100,000. So 30,000 for x plus 30,000 for y plus z equals 100,000. So clearly, z must be equal to 40,000. Good. So 30, 30, and 40. So they do add up to 100,000. So that seems to match up. 30 plus 30 plus 40 add up to 100,000. And we do have that the amount invested into the short term and the the short term and the intermediate term are the same. So that part matches up. So all we have to do to check it is to confirm that if we invest our money this way, we are expecting to get a 5.1% return. Right? So to check it, let's go over here and check this part of it. So So let's come over here and confirm. Let's check. Let me zoom into that. So check, and we're going to confirm that, in fact, if we have 0.04% times the amount invested into the short term, plus 0.05% times the amount invested into the intermediate term, plus 0.06% times the amount invested into the long term. Right? So then this one should be 30,000. This one should be 30,000. And this one should be 40,000. Okay, so 4% of 30,000. So some easy numbers. 10% would have just been 3,000, right? So then, therefore, 1% is 300. 1% is 300. So 4 times 3 is 1,200. So this is 1,200 plus 10% is 3,000, and half of 10% would be 1,500, plus 10% is 4,000, 1% is 400, 400 times 4 is 2,400. Good. And that adds up to 1,200, so that's 2,700, which adds up to 5,100. And 5,100 really is equal to 0.051 times 100,000, right? So you're getting an annualized 5.1% return. Check. Good. So invest solution is to invest 300,000 in 30,000 into both the short and intermediate term bonds, and 40,000 into the long-term bonds. With federal bonds, another really interesting thing that happens, that's not a good sign, is that there have been some rare points in time when the long-term bonds, 10-year, you're lending money to the federal government for 10 years or longer, that the return on that goes all the way down to 0, or that it becomes negative, right? So what does that mean? It means that at some point in time, somebody had money and they lent it to the government, and in exchange for lending the money to the government, they also paid the government money, right? Like they paid the government for the privilege of letting them borrow the money, right? Isn't that crazy? Like, do you guys want a loan from me to you? Here's $1,000, borrow it, and I'll also give you a bonus. Here's some extra money for borrowing it. It's really a strange phenomenon, right? It just means that those people were incredibly desperate to get rid of their money in some way and have somebody else hold on to it. Those have usually been bad times. Again, another bad indication that people are so uncomfortable with the way the economic landscape or the investment landscape is at that moment, that they would prefer to pay someone money to take their money from them and hold on to it, right? Presumably under the belief that you'll get it back, but that's usually a really bad sign. It's a great indicator that something bad in the economy is about to happen. And then you guessed it, it has happened recently. We hit we've hit either zero, close to zero, or maybe just barely peaked into the negatives very recently within the last year. So not another bad omen that potentially bad things are coming. So be prepared.
Thank you.
You're welcome. This reminds me of the movie Schindler's List. There was a scene, as I recall, there was a scene where some of the Jewish families that knew that they were going to be taken into custody and had no idea what was going to happen to them. They were like desperately looking for some of the wealthier families were looking for somewhere to invest their money, and then, of course, people took advantage of that and were buying gold from them, and taking their money and giving them really terrible returns, um, you know, on their investment. So negative interest rates, right? So they were handing over, $100,000, something really valuable, in the exchange for, you know, 10 years from now, I'll give you half of it back. you know, what you're giving them the opportunity to take all your money, all your gold, and you're crossing your fingers that 10 years from now they'll give you half of it back. That's a negative return. But in a time of war setting, in the unfortunate situation they found themselves, that was as good as it got. They really didn't have any other choices. Right? A lot of, and not just like shady characters in a back alley that were doing that. Banks were doing that. So profiteering was taking place all over. Anyway, it's a good movie if you haven't seen it. Okay. Any other questions on this one? No, no, no. I think the biggest thing people kind of get caught up with is the defining of the variables. Make sure that you take a moment and write them down, because if you don't write them down, as you get through this, it's very easy to get lost with all this stuff and forget what does X represent, right? So it represents a dollar amount. And so it's important to remember that it's a dollar amount, not an interest rate or not a time frame. It's a dollar amount, so that you can come up with these equations in a way that makes sense. Right? Also, if we make a little, accidentally make a little mistake with the calculations, we can catch it right away, right? limit is. We'll spend some time estimating limits numerically and graphically. We'll explore when limits fail to exist. And in this section, we'll talk about one-sided limits as well. Okay. Definition of limits. Before we get to the definition of limits, let's just look at an example, and we'll find it with our calculator if we need to. So consider the following. Consider just a simple polynomial function, f of x equals to, make it 3x squared plus 2x, I don't know, plus 1. Good. So this is a parabola, right? I can graph this. I can sketch it by hand if I convert it into the vertex form, right? Which means I'd have to complete the square and turn it into a different form so I can find the vertex, decide if it opens up, opens down. So a whole bunch of work can happen there, but I don't really want to spend too much time on that. Instead, I'm just going to get technology to graph this, and then I'll use that to think about the definition of a limit. Okay, so let's just use Desmos. Let's go over here. Desmos.com, graphing calculator, and I'm just going to graph this thing. So f of x, oops, f of x equals to 3x to the second power plus 2x plus 1. Okay, so there it is, a nice parabola just like we had anticipated, right? Okay, so what we're going to do is think about what happens to the output of a function, right? Where does the function go as the inputs approach that value from either direction? I don't know if I did a good job of explaining that. So let's put it this way. Like this. So let's look at specific points. For example, let's say that I want to know what happens to this function as it approaches, say, the value 0, right? So I'm going to consider points where the input is really, really, really close to 0, but never actually 0. I want to get close to 0 to see where it's heading, not the actual value there. So as the inputs get close to 0, so let's say, for example, I try 0.1. So let's see, as the input becomes 0.1, the output is this little dot right there, which is 1.23. Right? In fact, let me zoom in a little more. Here it is. As the input is 0.1, the output is 1.23. Now, I want to get a little closer. How about if the input was 1.05, 09, let's say. 0.9. Okay, so see, I got a little closer to 0. The input got a little closer to 0, and I can see that the output is now here at 1.2043. Okay, so let's get a little closer. 0.005. Now I'm a little closer. And here it is. The input is really, really close to 0, but I've made them positive this entire time, like that. So now the input is 0.005, and the output is here, right? So the output is 1.010075. So I can approach it in the other direction too, meaning that the input value approaches 0 from the negative direction. I can start at negative 0.01 or negative 0.1. If I input negative 0.1, negative 0.1 is over here, and then here is my output, 0.83. Good. And also input negative 0.01. And now my output is right there, really close, at 0.98. Good. I can get really close, 0.005. And now my output is 0.990075, right? In fact, if I zoom in a little bit more, it'd be easier to see. Let me lose track of the axes over here. But anyway, as you can see, as the inputs approach 0 from the left-hand side, the outputs get closer and closer and closer and closer to that value right there, right? And as I approach 0 from this direction, as the input value gets closer and closer to 0 from the right-hand side, the outputs are here. We get that point, and then we get that point, and we get closer and closer and closer to here. So hopefully we've convinced ourselves that as the input approaches 0 from either direction, the function value gets closer and closer and closer to 1. Good? Okay, so limits care about where is the function heading? Is it heading to a specific number? We never really consider what the function is at that particular point. So in this case, obviously, f of 0 is just equal to, well, how do I evaluate something here? F of 0? Oh, it's right here. It's equal to 1, right? If I just plug in a 0 here, 0, 0, well, the whole thing equals to 1. Okay, the actual value of the function happens to be 1 here, but the actual limit, when we're defining what a limit is, doesn't really take that into consideration. We don't really care what the function value is when we plug in the input of a 0. The limit cares what happens when we get close to 0, infinitely close to either direction. Where is that heading to? Okay. Does that make sense so far? Kind of, maybe? Okay, so let's look at the actual definition and see how that matches up. Oh, let me do a quick little sketch of what we just saw. So we had some sort of a parabola that kind of came like this and went like that, whatever. And then we had this. So then we had different input values. Let's call that input 1. We'll call that input 2. We'll call that input 3, like that, right? And then as I plug these inputs, right, this is like x equals to a sub 1, x equals a sub 2, x equals a sub 3. As we plugged in different input values, we were getting different output values, right? Like this one traced to, say, there. So this was the point a sub 1, comma, f of a sub 1, right? And then as I plugged in this one over here, this would have been a sub 2, comma, f of a sub 2. Good. And so on and so forth. There was also some values on the other side. As I approached 0 from the other direction, maybe this one over here would have been a sub 4, and then a sub 5. Good. And then they resulted in a little output over here. This one would have been a sub 4, comma, f of a sub 4. Right, that was this little point there. And then a sub 5, comma, f of a sub 5 would have been a little point over here somewhere. Okay, so as the inputs approached 0 from this direction, inputs, or 0 from this direction, right? We say that as x approaches 0. So this is the notation we want to adopt in this section. This little arrow like this indicates as x gets closer and closer and closer to 0, but never actually 0, right? That's an important distinction here. We don't really care what happens when we plug in a 0 into the function. I shouldn't say we don't really care, but that's not the focus of the definition of the limit. Okay? The limit cares about where is the function heading, where is the output getting closer to, closer to, closer to, as the inputs get closer and closer to 0. Good. And as we see, it all confirms that everything is heading toward an output of 1. right? These outputs were getting closer and closer to the 1. They were always close to 1, but a little bit bigger, the outputs. And in this direction, the outputs were always a little bit less than 1. They're getting closer and closer and closer to 1. So we would note that our function, we would say that the notation we're going to adopt here is that f of x approaches to positive 1 as x approaches 0. Let me erase this thing over here and put it. F of x approaches to 1 as x approaches to 0. Good. Or equivalently, another notation style we're gonna develop to represent this exact same thing is this one, the limit, so LIM, the limit as x approaches to 0 of f of x equals 1. Right? This is the same thing as this. F of x gets infinitely close to 1 as x gets infinitely close to 0. Good. So far we're okay. Any questions? No? No? Maybe? Sort of? Kind of? Okay, so this is the graph of this thing, and this is the y-axis and the x-axis. Okay, so now let's look at the official definition, see how it all matches up. So this is the, let me zoom in here, definition of a limit. So we write that the limit as x approaches to a of f of x equals to L, and say that the limit of f of x as x approaches a equals to L, if we can make the value of f of x arbitrarily close to L, so as close to L as we like, by taking x sufficiently close to a, but not equal to a. Right? So a little picture of what's going on here is very similar to the concrete example we just looked at. So if f of x is some, oh yeah, question? Is there a question, or just a mic thing?
No, just a mic thing.
Oh, okay. All right, so if we have some arbitrary function, here's some arbitrary function f of x, no specifics given. So let's say, just to give you a picture, so if we have some value a, let's say a is over here, what do I want it? Let's say it's here. Here is a. So a is leading to there, and so we say that this is capital L there. So this is the ordered pair a comma L, like that. Okay, so now we're going to consider what happens as the input value x approaches a from either direction. From either direction, as the inputs get closer and closer to the letter A, but never actually equal to A. We're not taking that into consideration. We're only considering what happens as you get closer and closer and closer to A from either direction. So as we input values here, let's call that x sub 1, let's call this x sub 2. As we do that, we see that the outputs of the function are going to begin to get closer and closer and closer to L, right, on either direction. This is x sub 4, this is x sub 5, we have x4, x5 there, right? So as the inputs get closer and closer to this letter A, which is a value in the domain of, well, I wouldn't say that, which is a value in the x-axis, then the outputs get closer and closer and closer to this value L, and if that's the case, then we would say that this is true. The limit as x approaches a of f of x equals to L. Okay. So roughly speaking, this says that the value of f of x gets closer and closer to the number L, as and closer and closer, number L as x gets closer and closer to the number A. Good. Any questions about this picture? No? This is x of 1, f of x sub 1 is this guy, right? And then this one is the second one and the third one, right? So as we get closer and closer and closer, as the inputs get closer and closer to A, the outputs, f of x sub 1, f of x sub 2, f of x sub 3, get closer and closer and closer to this value L. If that's true, in either direction, on either side of A, then we say that the limit exists, and we can write it this way. Good. An equivalent notation to this is to say that that f of x approaches L as x approaches A. Right? F of x gets infinitely close to L as x gets infinitely close to A. Good. Questions, 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 questions? Oh, it's right here. An alternative notation to the limit as x approaches to A of f of x equals to L is to write that f of x approaches L as x approaches to A. Notice that the phrase, but x does not equal A in the definition of the limit, right? Where is it? But really close to A, but not equal to A, right? So that's an important thing to point out there, right? The actual definition of the limit is independent of whether the function, what happens when you plug in the actual value of A into the function. Just like up here on this more concrete example with some numbers, I never really said, oh, let's just plug in a 0 and that's just going to give you your answer. We're going to explore limits and what you're allowed to do with limits, when you're allowed to, how you're allowed to find them. And there will be cases where you're allowed to plug that in. I know some of you have already explored limits a little bit, and you probably remember there are cases where you're allowed to just plug in the value, but that's not the official definition of a limit. We'll have to kind of explore when you're allowed to do that and when you're not allowed to do that, and what would you do in the cases where you're not allowed to do that. Okay? So far we're okay? Okay, so notice that the phrase, but x does not equal A in the definition of limit, this means that in finding the limit of f of x as x approaches A, we never actually consider the value of x equals 2A. In fact, f of x need not even be defined when x equals to A. The only thing that matters is how f is defined near A. So that means that here are some graphical descriptions of functions. Let's say you're given this function here, A, and you want to know the limit as x approaches to A of this one. Well, clearly it equals to L, right? This is very similar to what we just did. So here we would say that the limit, let me write it down. Well, okay, whatever. So if this is the function f of x, we would say that f of x approaches L as x approaches to A. Right? That's this one. It all works out. Okay, what about this one? Well, this is indicating that there's a little hole here. Let me zoom in some more. In case it's not super clear, it's pretty small. There's a little hole there, right? That means that the original function is indicating that when you plug in A into the function, you get this point, not that point, right? So maybe let's label it something else. Let's say ... This is equal to, say, m, right? So this is saying that f, well, let's call this a g. Well, that's fine. Let's stick to the f. So if this is the f of x function, all of it, right? Everything in red, including the dot, this is saying that f of A equals to m, right? Something that doesn't equal L. However, the limit is the same. The limit doesn't care about what happens or is independent of what happens at that specific value. As we let x get closer and closer to A, but never actually equal to A, as we let x approach A from either direction, the outputs are going to approach L, right? The outputs right? As this is, say, this is x sub 1 over here, it leads to that guy over there. And if this is x sub 2, then it leads to this guy over there. And as we get closer and closer and closer to A, but never actually A, all the outputs are going to be over here if the input is to the right of A. And if the input is to the left of A, say this is x sub 3, here is the output, and here's x sub 4, and then here's the output. Right? As we approach A from the left-hand side, as we approach A from the right-hand side, those outputs are still going to be approaching the letter capital L. Even though, according to my graph, at x equals to A, the output is M. That's okay. We still have the same limit. The limit of f of x still equals to L as x approaches A. Good. And same thing here. Here, since there's a little hole there and it hasn't been replaced by anything else, this is just indicating that the function is undefined at A. Right? So this is indicating that f of A is undefined. Here, according to this graph, f of A was capital M. And here, in this case, we were indicating that it was continuous at that point. So note that in this case, f of A was actually equal to L. Right? So here, f of A actually equaled L. Here, f of A equaled something else. And here, f of A was undefined. But no matter how you slice it, in all of these cases, the limit of the function was approaching capital L. Is that okay? Questions? Any questions? Any questions? Right. So if you're asking the value of the function at A, you care about what it is. What is it at x equals to A? If you're asking about the value of the limit as x approaches A, you don't really care what it is, you care what it looks like. Where does it look like it's heading? What does the graph indicate? Well, graphically, for solving this graphically. Where does it look like it's heading, not where is it actually heading? Good. And for the official definition, we need x to approach the value A from both sides to give you the same answer. Good. Any questions about this at all? No? So in all three cases, the limit as x approaches A of f of x equals to L. Right? So you can write it this way, or you can write it this way. No questions? Okay. So how do we find it? Well, one way to do it is to do it numerically or to graphically. How do we find these limits? So let's say, for example, we were given this one. Find the limit as x approaches to 1 of this function. I know that the first instinct is to plug it in. I don't know, plug in a 1 into there and see what happens. And what's going to happen if we do that here, so note, f of 1, right, assuming that this is a function, so let's say f of x is x minus 1 over x squared minus 1, and f of 1 is going to be blank minus 1 over blank squared minus 1, right, and let's put it in color. Put a 1 there, put a 1 there, put a 1 there. I end up with 0 over 0. 0 over 0, which is undefined. F of 1 is undefined. Okay, so it doesn't really give you any information, right? As we just finished pointing out, though, the limit doesn't really care what the value of the function is at 1. We care about what happens as you approach 1. As x gets infinitely close to 1 on either side, what is it going to approach? What is the answer going to be? So it's undefined when x equals to 1. But let's use our calculator to approach this by using a table. Right? Make a table of values and find your answer that way. So let's go to our calculator. Next. Okay, so quit from wherever you might be at. Clear anything. Let's go to mode and make sure that we're in function notation. That looks good. Floating road. Okay, so everything looks fine. Okay, let's go to y equals and type in that equation. So let's clear that guy. Let's clear that guy. And then let's wrap the numerator in parentheses, x minus 1, close parentheses, divided by the denominator, which is x to the power of 2. Oops. Okay. Okay. X minus 1, close parentheses, divided by x to the power of 2 minus 1. Okay, so hopefully that matches this up. That's what our function is. Okay, next I'm going to use a table. So I'm going to go up here where it says table set. See, table set. Second table set. I don't care about that. It doesn't matter what that number is. So right here it's blinking a 0. It doesn't matter. That doesn't matter either. It doesn't matter. But what I want to do is go down here, and where it says independent, I want it to say ask, and where it says dependent, say auto. Okay, if it's not like that, use your arrows to come down here, choose whatever you want, and then hit enter. So make sure independent variable is under ask, dependent is under auto. Okay, I got there by doing table set, second table set. Good. Once you have it in this order, next I'm going to go over where it says table, right above graph. So second table, and then whatever's in there, just hit delete, 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 the whole thing. Clean slate. Okay, so what this is going to be a table that automatically evaluates these things. So if I hit a number, like let's say I hit 2, it's going to do 2 minus 1, that's going to be a 1 in the numerator. And then it's going to do 2 squared minus 1, that's going to be a 4 minus 1 is 3. So this will be equal to 1/3. Okay? 1/3, 0.333333. Right? So this is a place where I can just evaluate this function for different values. Good. And remember that I want to know what happens as x approaches 1. If I just hit 1, I'm going to get an error, right? Because that's an undefined. I'm getting a 0 over 0. That's an error. So it's not good enough for us to just type in a 1 in there. What we got to do is get close to 1, but never actually 1, right? We care about where the function is heading, not the value of the function at that point. So let's get close to 1. How about 1.1? That's pretty close. How about 1.01? That's really close. How about 1.001? That's seriously close to 1. Okay. All right, what about in the other direction? How about I approach 1, but from the left-hand side on the number line? So let's say starting at 0.9, that's close to 1. Or how about 0.99? That's even closer to 1. Or how about 0.99999? Now I'm really close to 1. Okay, and remember that there's some rounding issues that can happen with your calculator, so I take it back. Let's go up here and not get that close. Our calculator can't handle it. Say 3 nines. Okay. Right, so as I approach 1 from the left-hand side, I get closer and closer to 1 from the left-hand side. Here are my outputs. They seem to be getting closer and closer to 0.5. And as I approach 1 from the other direction, 1.1, 1.01, 1.001, they seem to be approaching 0.5 from the other direction as well. So from this work, I feel sufficiently happy concluding that this limit is going to be equal to a half. Is there any questions about that? This isn't a formal proof. It's not like I've proven this is true, but I feel pretty good. Like, it's a pretty solid justification. It's not 100% solid, but you know, it's pretty good. Sometimes pretty good is good enough. Keep in mind though that sometimes weird things, rarely, but weird things can happen. It's possible that your calculator might be lying to you. There are some cases where we might fool ourselves into thinking we know the answer, and we'll explore a couple of cases like that in a little bit. Okay, but for now, I feel fairly confident that the answer is 0.5. Also, what I could do is graph this thing. So let's go to my window, and okay, I know I want to get really close to 1, so I don't want to go from negative 10 to 10 for the input. Let's go from 0 to 2. 0 to 2. And I know my output, I'm kind of cheating a little bit. I know my output was a half, so I don't want to go all the way from negative 10 to 10. Let's go from 0 to 1. That should capture the output I want. Okay, let's see what that graph looks like. There it is. Okay, so I can use trace and see that little blinking guy right there. That tells you the ordered pair where it's blinking. So I can kind of travel along it. Oh, there we go. Okay, so here is the input values of point H3, and there goes the output values. And as I get closer and closer, as this input value gets closer and closer to 1, the output values get closer and closer to 0.5. And then when I go over it on the other side, let's go to the other side. From the other side, as I approach it from this way, the input values are getting closer and closer to 1, but from the other direction, the output values are getting closer and closer to 0.5. So graphically, I'm also pretty happy in concluding that this whole thing is approaching 0.5. Again, still not a formal answer to this question. We'll get to a formal answer in a little bit. For now, I feel fairly confident, pretty happy with concluding that the answer must be equal to 0.5. Any questions about that? No? No? Okay, so let's see what we have here. So we did something like this. We created a table on our calculator, and we were able to conclude that as we got closer and closer and closer to 1 from the left-hand side, the outputs were getting closer and closer and closer to 0.5. And as we approached 1 from the right-hand side of the number line, the inputs were getting closer and closer and closer to 1, but never actually 1. The outputs were getting closer and closer to 0.5. So from the table, I felt pretty happy concluding that the output was approaching 0.5. And then we also did a rough graph, right? I don't think they have a graph here. Do they have a graph? Oh yeah, they did do a graph. Look, and so in the same way, we did something like this, where we have we graphed the function on our calculator, and then we just played around with the zoom and the trace and played around with it, and it felt pretty accurate to conclude that as we played around with our trace value, the outputs were getting like this. We're getting closer and closer and closer to 0.5 from either direction. Right? As the input approached 1 from the right-hand side, so this is x approaching 1 from this direction. So since it's approaching it from this side, we write it like that. And then here, x was approaching 1, but it was approaching it from the left side, so we write the left side. Little minus. Good. We'll introduce that notation in a little bit. Any questions about this so far? No? 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 Limits that fail to exist. All right, so everything works out wonderful and great when we have nice, pretty equations, but some ugly stuff can happen. Let's look at some examples when things don't work out quite so well. So there's this really simple example where we have the function output equal to 0 whenever we have a negative, and then starting at 0 or larger, the output jumps to 1. Right? So this is a function that can be used to represent lots of things, and one of the famous things that it represents is current, right? Switching an electrical current, switching it on and off at a particular point. So it's just a binary thing. So it's surprisingly common that we run into this kind of a graph in math. Okay, so let's explore the limit at x equals to 0, right? The limit at h equals to 0. So that actual value, h of 0, if we just plug in 0 into that, 0 is part of this set of instructions, right? It's a solid dot there. So h of 0 equals to exactly 1, right? So that's true. But what about the limit? Does the limit equal to 1? Well, as the input value, and this is a little mistake because we're just so used to x's and y's. Why did they jump over to h and t? All right, well, I think that this was a mistake. They really meant to put a t, right, because we're inputting t values, and the outputs are h of t's. H of t values are the output values. Okay, so as t approaches to 0, as t gets closer and closer and closer to 0, this way, closer and closer and closer to 0 from the right-hand side, then the output values are going to be, well, they're always 1. Very consistent, they're always 1, right? So like if this one is, I don't know, no, that's fine. If this one is t sub 1, let me just zoom in a little more. And erase this thing. So like if this one is t sub 1, then the output is 1. And if this one is t sub 2, the output is 1. Right? So as we approach 0 from the right-hand side, the outputs are always positive 1. However, in the other direction, like if the input is t sub 3 over here, then the output is 0. And if this one is t sub 4 over here, then the output is 0. So as t approaches to 0, but from the left-hand side, the outputs are always going to be 0. Good? So they don't match. In order for the limit to exist, in order for you to say that the limit exists, it must be true that as t approaches that number from either direction, that it gives you a specific answer. It gives you a specific value L, right? So going back to the more sort of generic description of what a limit is, remember if we had some function f of x, we would say that at a, the limit is L, if it was true that whenever we inputted new values getting closer and closer to a on either side, that the output functions would get infinitely close to that value L on either side, right? So we would write that if this was what it would look like, we would write that the limit as x approaches to a of f of x equaled L, right? Or we would say that f of x approaches L as x approaches a from either side. But that's not the case here, right? Here, the as t approaches 0 from the left-hand side, then h of t goes to 0, and as t approaches 0 from the right-hand side, h of t approaches 1. They don't match. So we would say that the limit does not exist here. Any questions about that logic? As t approaches 0 from the left-hand side, h of t approaches 0. As t approaches 0 from the right-hand side, h of t approaches 1. So we would say that the limit does not exist. There is no single number h of t approaches as t approaches 0. Therefore, the limit as t approaches to 0 of h of t does not exist. Any questions about that logic? No, no, maybe, sort of, kind of, maybe, sort of. Okay, but then we can't say that the limit exists. It does not exist. But we can get a partial answer. We can say that the limit exists in one direction, right? So we define this idea of one-sided limits now. So we noticed in this last example that as h of t approaches 0, that h of t approaches 0 as t approaches to 0 from the left-hand side, and h of t approaches 1 as t approaches 0 from the right-hand side. So we can use this indication to point out that a more a limit from the left-hand side does exist, and a limit from the right-hand side does exist. We would still say that the limit, just kind of generically saying the limit still does not exist. But the limit as t approaches to 0 from the left-hand side does exist, and it equals to 0. And the limit as t approaches to 0 from the right-hand side of h of t does exist, and it equals to 1. Okay, so that's where we introduce this little notation of a little minus here in the top right-hand corner to indicate that we are only considering inputs that get infinitely close to this number, but always approaching from the left-hand side on the number line. It just so happens in this example that that means that they're all negative numbers, but that's not necessarily true. If we were considering the limit as t approaches the number 8, then 8 with a little minus here just means that you would be approaching from the left-hand side of a number line. So like 7.9, 7.99, 7.99999, right? It doesn't necessarily mean that it's a negative number. Good. And putting a little plus sign there on the top right-hand corner indicates that we are considering values that are getting infinitely close to this number, but are always just a little bit bigger, right? Approaching from the right-hand side of the number line. Good. Any questions, any questions, any questions? No, no, no. So looking back on this thing, right, we would say that the limit as t approaches to, so the limit as t approaches 0 from the left-hand side of h of t equals 0. Right? So if we just restrict ourselves to cases that go this way, right, approaches 0. The limit as t approaches 0, but always from the right-hand side, h of t, well, they always equal 1, right? If we just restrict our inputs to be values that approach 0, but always from the right-hand side of 0, then the outputs always approach 1. However, if we don't include this little restriction right here, we're restricting it. We're saying that the inputs are always to the left of 0. And here we're saying that the inputs are always to the right of 0. If we remove that restriction and just say what's the limit as t approaches to 0 with no restriction of h of t, the answer is does not exist. Does not exist. Right? Good. We restrict that restriction, it doesn't have a limit, right? Because it approaches different values from different directions. Good. Any questions? Any questions? Any questions? No, 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 no. Okay, so here's the more formal definition of a one-sided limit. We write that the limit as x approaches a from the left-hand side of a little minus, right? So always, the inputs are always going to be a little bit smaller than a to the left of a on the number line of f of x equals to L. And we say that the left-hand limit of f of x approaches, of f of x as x approaches to a. Is equal to L if we can make the value of fx arbitrarily close to L by taking x to be sufficiently close to a and less than a, always less than a. And again, just like in the full definition, the standard definition of a limit, not the one-sided definition, we don't actually consider what happens at a. Okay. So here's a nice little graph of the same thing. Similarly, we require that x be greater than a, and we get that the right-hand limit of f of x as x approaches a is equal to L, and we write it this way. Okay, so here is our function f of x. There's a nice little picture for it. And then we have the value a. And so as x approaches a, but always from the left-hand side, the outputs seem to be approaching this value here, whatever this is, right? So we labeled it L. So this is some height value L. So the limit as x approaches a from the left-hand side of f of x equals to L. And then in this direction, as x approaches to a, but from the right-hand side, then we'd say that f of x equals to L. So I think it's unfortunate that they use the same letter in both directions. It might give you the false impression that that means that they're always equal the same output, but they don't necessarily mean that, right? So there's two different definitions, not necessarily meaning the same output. Good. So I just would have used a different letter here. Good. Okay. By comparing the definitions of the two-sided and one-sided limits, we see that the following is true. The limit, right, no restrictions, as x approaches to a of f of x equals to L, if and only if it's true that the left-hand limit of f of x equals to L and the right-hand limit of f of x approaches to a on the right-hand side of f of x equals to L, right? So if the left-hand limit and the right-hand limit of f of x both equal to L, it must mean that the function the limit of the function f of x equals to L, right? If and only if means that if this is true, then these two are true, or the other way around. Right? So we have this sort of pair here, and then we have this thing here. So if this is true, then that means this is true. Or the other way around, if these are true, then that means that's true. Right? If the left hand and the right hand limits are different, the two-side limit does not exist. If they are the same, then that means that the limit does exist. Any questions? Maybe sort of come, sort of. Okay, so here's some some examples from a graph to make sure that we're getting this. So here is the function g of x. G of x is everything that's red, right? All of the red is the g of x. So the function looks to be doing this over here. Then there's a little hole. It jumps down here. There's still a little hole. And then it comes over here. There's a little hole and then equals to this. Okay, so let's look at some of these. What is the limit as x approaches to 2 from the left-hand side of g of x? So here is 2. As the input values get closer and closer and closer to 2, but always from the left-hand side, looks like the output is reaching 3. Okay. As the inputs get closer and closer to 2, looks like the outputs are going to be doing this. Okay. So we'd say that the limit as x approaches to 2 from the left-hand side of g of x equals 3. Right? And it doesn't matter, right? So note, they didn't ask me this, but note that g of 2 is undefined. Right? But it doesn't matter. We don't really care about that. Good. What about x approaches to 2 from the right-hand side? The limit as x approaches to 2, but from the right-hand side of g of x is equal to. Okay, so if we only focus our attention to input values that are getting close to 2, but always to the right of it, then the output values are getting closer and closer and closer and closer to 1. Good. So the limit from the left-hand side approaches the left-hand limit of g of x approaches 3. The right-hand limit of g of x approaches 1. So what's the limit at 2? The limit as x approaches to 2 of g of x does not exist. Good. Because the left-hand limit and the right-hand limit don't match. They go to different places. Therefore, we would just say the limit does not exist. But the way it doesn't exist is that the left-hand limit does not match the right-hand limit. The left-hand limit exists, the right-hand limit exists, but they don't match. Therefore, we'd say that the limit does not exist. Good. Okay, so for part B, now we're considering what happens at 5. So at 5, note that g of 5 does exist, and it equals to 1. Okay, now if we do the limit as x approaches to 5 from the left-hand side of g of x, so if we're just focusing from the left-hand side, we get closer and closer to 5, we're going to get these, we're going to get values that are getting closer and closer and closer to 2. So this equals to 2. Okay. And the limit as x approaches to 5 from the right-hand side of g of x, right? Numbers that are a little bit bigger than 5, they seem to be getting closer and closer and closer and closer to 2. And now they match. So now we would say that the limit as x approaches to 5 with no restrictions, left side, right side, no restrictions, of g of x equals to 2. Even though the actual value of the function at 5 equals 1. That doesn't matter. We care about what it looks like, not what it is. And it looks like it's heading toward 2, even though the actual function is evaluated at 1 when x equals to 5. Any questions? Desmos has a couple of nice little things like that to play around with. So here is a little graph that indicates that, right? So here is our function in red. Everything red is the function. And if we think about what happens at 1, the function is valid at 1. It's defined to be, looks like a half, right? So if we were asked what is f of 1 is about a half, okay? The limit as x approaches to 1 from the left-hand side, as the inputs get closer and closer to 1 from the left-hand side, you see the outputs are approaching 2. So the left-hand limit does exist as x approaches 1, and it equals to 2. It's heading toward 2. Good. Let's try here. On the other side, what about as x approaches to 1 from the right-hand side, we see that the outputs are getting closer and closer and closer and closer to 3. Right? So the limit, the right-hand limit does exist, and it equals to 3. Good. What is the actual value at x equals to 1? It's about a half. Right? So the left-hand limit, the limit as x approaches to 1 from the left-hand side equals 2. The limit as x approaches to 1 on the right-hand side equals to 3. But the actual value of f of 1 equals to a half. Right? And then, as we just noted, the left-hand limit exists, the right-hand limit exists, but they don't equal each other. Therefore, if you were just asked what's the limit as x approaches to 1, we would say does not exist. Let's see anything else. What about this one? What is the y value of the function? Okay, so the limit as x approaches to 3 from the left-hand side looks like from the left-hand side, the left-hand limit approaches -1. The right-hand limit as x approaches to 3 from the right-hand side is always 2. So the left-hand limit exists, the right-hand limit exists, but they don't equal each other. So we would say that the limit does not exist at x equals to 3. Okay, that's all I want to play with. Alright, I think you get the point. Okay, moving on. So here we have those, here we have that, and that's all we have for this. Okay, so it's easy as that. Let's look at some of the exercises in the homework. See if there's anything tricky in there. Go away. 13, 13. So far, not bad, right? Calculus isn't going to be hard. Review. 13.5. 13. 13. There we go. Okay, so let's see what kind of questions the book can ask you in 13.1. So sometimes you'll be asked to do things with tables. That's easy to do, right? Put it in your calculator, type it in your calculator. We did an example like this. And then you get to type in the values for x so that you can find your outputs. And hopefully from that you can be convinced of where the function is heading as the inputs get closer and closer to the value indicated, right? Now there's no restrictions on the left-hand limit or right-hand limit for either of these. So that means you have to approach in both directions. And they went ahead and helped you out by beginning the table in both directions. Okay, so those problems should be nice and easy. Estimate the limits numerically and graphically, use tables. Okay, so same thing, they just didn't provide you with this table, they just kind of expected you to do it on your own. So type this into your calculator in the function, go over to your table, and start plugging in values that are really close to -4. Right, so on either direction, -4.01, -4.001, or -3.99, -3.99999. Get really, really, really close and see if you can be convinced that the limit exists for those. Okay, so those shouldn't be too bad, right? Good. What about these? Okay, here they give you a graph and you have to just interpret the graph. We just finished doing something similar to this. So say, for example, number 18. What is the limit as x approaches 0 of f of x? So here's 0. As x approaches 0 from the right-hand side, looks like it's approaching 3. And as x approaches 0 from the left-hand side, looks like the output is also approaching 3. So we would say that the limit as x approaches to 0 of f of x equals to 3. Good. What about as x approaches to 3 from the left-hand side, f of x will approach 4. Right? As x approaches 3 from the from the left-hand side, the outputs approach 4. As x approaches to 3 from the right-hand side, the outputs approach 2. So the left-hand limit exists and it's equal to 4. The right-hand limit exists and it's equal to 2, but they don't match. So we would say that the limit as x approaches 3 does not exist. Good. And f of 3 equals to 3. Any questions, any questions, any questions? No? So far it's pretty easy, right? No major headaches. Again, more fun with reading graphs, And then these guys use a graphing device to determine whether the limit exists. If the limit exists, determine the value. Okay, so they're just asking you to create your own function on your own technology, potentially calculators. You can also use Desmos. And then you can either use the tables on your calculator, just like before, to convince yourself of what that limit is or should be, or the graphs. Good. So far, pretty easy stuff. Good. All right, let's take a little break. We'll come back. We'll look at 13.2. Okay, moving on to Chapter 13, Section 2. We're going to continue with our exploration of limits and find out some of the rules of limits, some laws and what you're allowed to do, what you're not allowed to do, what makes sense and what doesn't make sense. And in order to do that, I think we should kind of explore what could go wrong. In 13.1, we did a lot of really simple examples that are really intuitive. And that's important. That's an important initial step to begin with the really easy, obvious answers so that you get a good understanding of the fundamental ideas there. But the drawback of that is that it makes it seem like everything is simple and pretty and there's no problems. And that can get you a false sense of security, and that you get yourself into trouble, right? That's usually when people get into trouble, when they know just enough to be dangerous. So it gives you this false sense that you can just easily figure out anything and that there's no problems. Okay, so let's look at before we dive into what you're allowed to do. Let's consider a couple of things with our functions. So again, we looked at a really pretty simple example, so let's say example, consider we had something similar to this already. If we had f of x equals to, let's just say x squared. Simple, straightforward function. We know it's a nice, pretty parabola. If we graph this, I know it'll go up that way, and up that way, and up that way. And we can consider what happens as x approaches to, say, the number 2. That goes that way, and we know that that's going to lead to 4, right? So we'd say that the limit as x approaches to 2 of the function f of x equals to 4. Right? And we also know that the limit as x approaches to 2 from the left-hand side of f of x also equals to 4. And of course, that also means that the limit as x approaches to 2 from the right-hand side also equals to 4. Okay, so this was, again, a nice, simple type of example, something we saw already in 13.1. But what can go wrong? Things that go bump in the night. Consider, how about an example that has f of x equals to 1 over, 1 over x. Well, if we graph that, that's one of our standard functions. If we graph it, it looks like this. Goes that way and that way. So we have kind of a weird thing that happens here. So this goes off to infinity, right? It has a vertical asymptote at x equals to 0. So this is the x-axis, this is the y-axis. So what happens as x approaches to 0? Well, the limit as x approaches to 0 from the right-hand side goes up to positive infinity, and the limit as x approaches to 0 from the left-hand side approaches negative infinity. In fact, let's make this a little bit different, just so we don't deal with that. Let's deal with making it squared, which means that it equals to positive infinity in either direction. So it goes like that in either direction. So now, as x approaches to 0, as x gets closer and closer and closer and closer to 0, as x approaches to 0 from the right-hand side, and as x approaches to 0 from the left-hand side, either way, the outputs are getting infinitely large, right? So it's not going to exist. But it's not going to exist, the limit is not going to exist in a very special way. It's not going to exist because it goes off toward infinity. The limit, the limit as x approaches to 0 of f of x, well, we say equals to infinity, meaning that it gets infinitely large, right? And so that means it doesn't exist, and it doesn't exist in a special way. It doesn't exist in that it just gets infinitely large. Good? Any questions about this? No. So there could be an asymptote. That's something we have to be careful about. And then there could be another weird kind of situation. What if we had a function, say g of x, equal to sine of pi over x? Right? What does that look like, and what should we get? Okay, so let's graph this thing to see what it looks like when we graph it. So let's just go to Desmos. Well, g of x equals to, come on, equals to sine of pi divided by x. Look at that crazy thing. Where's the next one? Okay, look at this crazy thing. Look what it does. The function oscillates, because it's a sine function, so I know it's going to oscillate between -1 and +1. But then the period starts oscillating faster and faster and faster and faster, right? The closer we get to 0, the closer x gets to 0, the faster and faster and faster it oscillates. Good? Okay, so the tricky thing about this is that there exists the following thing. I can come up with a very specific choice of inputs such that the input always equals to, say, for example, +1. If I chose the input to be 0.4, I would get 1. And then if I chose the input to be 0.222, the output would be 1. And if I chose then the input to be 0.1538, the output will be 1. So if I choose all of these values up there, kind of very, very strategically pick these inputs, very, very strategically pick that as our input value there, that guy 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 there, then what happens is that there exists a path along the x-axis such that that path is getting closer and closer to 0, and the outputs always equal 1, so we can trick someone into thinking that the limit will approach 1. Does that make sense? In fact, I can do that with any of them. So say 0. There exists a path towards 0, the inputs approaching 0, right? I can choose this guy. Oops. Come on. I can choose this value right there. Then I can choose this value right there, and then this one, and then this one, and then this one. So there exists a very specific path that I can choose so that the inputs are getting closer and closer to 0, and the outputs are also getting closer to 0, so I can trick someone into thinking that the limit equals 0. Right? And same thing with -1 down here. There exists a unique choice of inputs, right? Like I can choose it to be this guy down here, and then this one, right? There exists a unique choice of inputs such that the outputs all give you -1. So someone might be convinced that the answer is that. So we have to be careful, right? So the whole point of this is you have to be careful of what you're doing, because you might accidentally get the wrong answer. So let's see if we can get a thing going here. For example, if we let x equal to 1, then we're just going to get pi. Sine of pi is 0. Okay, that's 0. And also sine of 2 pi is also going to be 0. Right? So if I put 1 divided by 2 here, 1 divided by 2 in the denominator gives you sine of 2 pi. Put that over here. Right? If I have x and then I have 1/2, and this is sine of pi over x, this is going to be sine of pi over 1/2. So this is going to be equal to sine of 2 pi. Okay, so this is going to give me a 0. The next time I get a 0 is going to be at 3 pi. Oh, so if I put 1/2 here, I'm sorry, 1/3 there, then sine of pi over 1/3 is equal to sine of 3 pi, which gives me 0. Good, and the next one's going to be 4 pi and 5 pi and 6 pi. So if I choose these to be these kinds of fractions, I'm always going to get 0 as the output, right? And so I'll have a case where this is heading towards 0, right? These fractions are heading towards 0, and the output is always 0, so someone might get the false impression that the limit equals to 0. Is that clear so far? So let's try 1/3, 1 divided by 3, yep. 1 divided by 4, yep. 1 divided by 5, yep. 1 divided by 6. Look at this, I'm getting closer and closer and closer to 0, and the answer is always 0. So someone might falsely conclude that this limit equals to 0. Is that clear? Clear, 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 clear. Okay, on the other hand, I can do the exact same thing. Let's do a table. Let's do sine of pi, divided by x, okay. On the other hand, say 1. When does it equal to 1? It equals to 1 at pi over 2. So if we let x equal to 2, we'll get a 1. Okay. We also need it to approach 0. So what do I need it to be? So we have x, and we know that if we let this equal to 2, we'll end up with sine of pi over x will be sine of pi over 2, which is equal to 1. And pi over 2. So the next place that it equals to pi over 2, equals to 1 is at 2.5 pi, so 5 pi over so pi over 2 plus 2 pi is going to be equal to pi over 2 plus 4 pi over 2, which is equal to 5 pi over 2, which is going to be equal to pi divided by 2/5. Good. So this is 2/5 is what goes there. Right? So if I plug in sine of pi over 2/5 and multiply the numerator times the reciprocal of the denominator, this is going to be equal to sine of 5 pi over 2, which is also going to give me 1. Okay, so then if I made it made it to the next one, what would I need the next one to be? Pi over 2 plus 4 pi, which is going to be pi over 2 plus 8 pi over 2, which would be 9 pi over 2. Okay, so then that's the same thing as pi over 2/9. Oh, okay, so over here, if I plug in 2/9, sine of pi over 2/9 is equal to sine of 9 pi over 2. Oh, this is a pi. 9 pi over 2. 9 pi 2 also equals 1. Good. Okay, I start to see a pattern if you think of putting a little 1 there. Looks like it's a fraction where the numerator is always a 2, and looks like in the denominator we add multiples of 4. 1, 5, 9. My guess, if this is going the right way, the way I think it's going, I think the next one's going to be 2 over 13, and then 2 over 17, and so on and so forth. And these should all be values such that they are approaching 0. Again, that the inputs are heading towards 0, but I've cherry-picked the right ones so that the output always equals to 1. Right, so let's see if Desmos agrees. So 1 divided by 5 gives me a 1. And 2 divided by 5, and 2 divided by 9 gives me a 1. And 2 divided by 13 gives me a 1. And 2 divided by 17 gives me a 1. So here I have another path towards 0. I've chosen all these paths towards 0. Oops. Zoom out. Zoom out. Right? Oh, I didn't even notice. I also forgot to point out that the ordered pairs were there. So anyway, so here I have another path towards 0. The inputs are getting closer and closer and closer to 0, but the outputs are always 1. So there's that one and that one and that one and that one, and I can just keep going, right, forever. So again, I can give someone the false sense that the limit will be equal to 1. Right? If someone is just looking at this table, they go, man, I keep approaching 0, I'm getting closer and closer and closer to 0, and the output is always 1. So someone might look at this and conclude that the limit as x approaches to 0 of sine of pi over x equals 1, right? But then we know that that's wrong. And also, by just looking at these table values, someone might get the wrong impression that the limit as x approaches to 0 of sine of pi over x equals 0. And again, that would also be wrong. Good? Okay, so my point in all of this is that functions get tricky. They're tricky little things, and so you have to be very careful about what you do and what you're allowed to do, not allowed to do, when you're solving these. Otherwise, you might be tricked into thinking you know the answer when you really don't know the answer. Good. Any questions about any of this? No? So clearly the limit should not exist, right? By looking at the graph, right, we should know that the limit as x approaches to 0 of sine of pi over x, the limit should be does not exist. Does not exist. Right? Because it oscillates back and forth between -1 and 1, -1 and 1, -1 and 1. It just oscillates back and forth. It never settles onto a specific value. If the limit were to exist, it would mean that as you get infinitely close to the 0, that the output of the function gets infinitely close to some specific constant. That's not the case here. Good? Good? Okay, so because there exists things that might trick you, right? Like this, there are tricky things out there. And because of other cases like this one, there might be an asymptote, or it might be something that oscillates infinitely. We have to be careful about what we're allowed to do with limits and what we're not allowed to do with limits. And that's what this last section will cover, some of the rules of the road of limits. All right, so let's get on to that one then. Okay, so 13.2. So limit laws, we're going to be applying some of those limit laws. Finding limits using algebra and the limit laws, and then using left and right hand limits. So limit laws. These are the rules of the road, the things you're allowed to do with limits. Make sure that that you understand each of these and we apply them properly, and that we don't extrapolate to some other rule that's not explicitly outlined here. Okay, so if we have this, the limit as x approaches to a of some function f of x, and the limit as x approaches to a of some function g of x, so suppose that c is a constant and that the following limits exist, right? So this exists, and the letter c just represents some constant. So the limit as x approaches to a of the addition of two functions can be broken down this way, so that we can find the limit of this function, the limit of this function, and then add them together separately. Same thing with subtraction. If there's a difference of these two functions, we want to find the limit of the difference. It's equal to the difference of the two limits, right? So what this allows you to do is to find them separately and then subtract them. Okay? There could be a constant times a function. We can kind of take out that constant, figure out the limit of the function, and then multiply it by the constant. If we have a multiplication of two functions and we want to find the limit as x approaches to a, then we can find the limit of one of the functions, find the limit of the other function, and then multiply them together. Right? That's what this is telling us. And then if we have a fraction where we have the limit of this ratio of this fraction, then this tells us that we can find them separately. Find the limit of the numerator, find the limit of the denominator, and then divide them, provided that we don't accidentally divide by 0, right? We cannot have a case where the limit as x approaches to a of g of x equals to 0, because then we'd be dividing by 0. Good. Okay, that's just explaining everything I just talked about. Okay, and then two more. The limit as x approaches to a of f of x to the power of n. So here the power of n is just applying to the f of x, right? And that this law is telling us that what we could do is first find the limit of the function and then raise it to the power of n. It's just sort of in the order in which you do things. Some people also think of this as bringing the limit inside the parentheses. You can bring it inside the parentheses. Same thing with this. This is indicating that in order to find the limit as x approaches to a of the nth root of x, right? This nth root only applies to this f of x here. Then what we could do is first find the limit of f of x, find an answer, and then apply it to this nth root. Again, people often think of this as bring the limit inside, right? Bring it inside the radical, and that's just a sort of different language for the same thing. We're going to first find the limit and then take the nth root. So really what we're doing is just establishing that we can do things in a different order. Here they're saying take the f of x function, raise it to the power of n, and then find the limit. Whereas we're saying, no, it's just if we want to, we're allowed to first find the limit and then raise it to the power of n. Good. Okay, so using those limits, those laws of limits, let's use them in this application. So here we have a little graph that describes the f of x function, that's the red one, and the g of x function, that's this blue one over here. So based on this graph, we can find the individual limits, and coupled with our rules for our laws of limits, we can find these things. Okay, so the way it's written, see this right here is saying that the f of x function needs to be multiplied by 5 and then added to the f of x function. The g of x function needs to be multiplied by 5 and then added to the f of x function. And then once you have that new function, find the limit as x approaches -2. Well, we don't want to do that. Instead, we want to use our properties to simplify this into something we can do in a much easier way. So for part A, we want to say that the limit as x approaches -2 of g of x plus 5 times g of x, right? One of our properties said that we can find the limit of f of x, find the limit of the 5g of x, and then add them together. Is equal to the limit as x approaches -2 of f of x plus the limit as x approaches -2 of 5 times g of x. Good. That's property number 1 up here. We have a summation. We can separate it this way. The limit of an addition, the limit of a sum is equal to the sum of the limits. Good. Now we're going to use property number 3, that the limit of a constant times a function is equal to the constant times the limit of the function. Right? We can factor out the c, something, another way to look at it. Bring out the c on the outside. So now we want to take this 5 on the outside and say that this is equal to the limit as x approaches -2 of f of x plus 5 times the limit as x approaches -2 of g of x. Good. Okay, so now this is something I can find from my graph. See, the graph gave us the graph of f of x and the graph of g of x. It did not give me the graph of f of x plus 5g of x. I can't directly find what happens when you plug in a -2 into here from the graph because they didn't give me that graph. Okay, but they did give me the f of x graph. That's the red one. What happens as x approaches -2? As x approaches -2 from either direction, looks like the limit is going to be equal to +1. Okay, here's -2. As x approaches -2 from either direction, looks like the function is approaching 1. I don't care what happens at x equals to -2. I care what happens as you get close to it. Okay. Plus 5 times the limit of g of x. Okay, so as we approach -2 from either direction, the g of x function looks like that's approaching -1. -1. Good. So we end up with 1 minus 5 or -4 as our answer. Any questions, any questions, any questions? No? No? Okay, part B. Put B over here. It says the limit as x approaches to 1 of, and now we have the multiplication of f of x times g of x. And so one of our properties says that if we're multiplying two functions, and we want to find the limit, then we can find the limit of each one of those functions separately, the limit as x approaches to 1 of f of x, find that limit, and multiply it times the limit as x approaches to 1 of g of x separately, and then multiply them together. The limit as x approaches to 1 of f of x is going to be a 2, and the limit as x approaches to 1 of g of x, oh, we have a problem. As x approaches to 1 from either side, g of x approaches to -1 in one direction and approaches to -2 in the other direction. This does not exist. Does not exist. So I have a 2 times a does not exist, so the whole thing does not exist. Good. Questions, questions, questions? So far I have that for this one, the answer was -4, and for this one, the answer is does not exist. Good, 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 good. Okay, part C. Let's put C over here somewhere. Part C. We have the limit as x approaches to 2 of this fraction, f of x over g of x. Good. So one of our properties indicated that we can separate this into a giant fraction where we find the limit of the numerator, find the limit of the denominator, and then add them together. So as x approaches to positive 2, the f of x function will approach that guy there. So I don't know, that looks like maybe 1.5, say 1.5, which is 3 over 2, 1.5, 1.5. Okay, and the limit as x approaches to 2 of the g of x, oh, that's going to be a 0. Good, so this is undefined. Good. And then D, let's squeeze it over here. Let's put D over here somewhere. D, we have the limit as x approaches to 1 of f of x raised to the power of 3. So we have a property that says that instead of cubing f of x first and then finding the limit, let's find the limit of f of x first and then cube it. Find that limit and then raise the whole thing to the power of 3. Good. So the limit as x approaches to 1 of our function, well, that's going to be, looks like it's a 2. Good. And then we cube that whole thing, and so the whole thing will be approximately 8. Good. So the limit as x approaches to 1, the output is approximately 2. So that's where we get this. Questions? See what the author did for these guys. So they end up with a, yep, same thing we did. A 1 and then a -1. So then we get this. For B, we got negative. Can exist because the left hand and right hand elements are different. Okay. What is it for B? What was the question for B? Limits are different. 1. Oh, the g of x does not exist. Got it. Okay. Yep. That's what the author got. And then an 8. Yep. Same thing. Any questions? Does not exist for different reasons. Does not exist, and here we got an 8. Any questions? Okay, let's look some other problems. Applying the limit laws. Okay, so here are some really common applications of limit laws. Okay, so the limit as x approaches to the value a of c equals c, right? And this one's a little tricky because there isn't even an x value, right? So this is just a constant. The function equals a constant. So, for example, if we let the function f of x equal to the number 8, for example, then this is just going to be a horizontal line, right? This is just a line that looks like this, right? Otherwise known as y equals to 8. It's just a horizontal line. Here's y, here's x. So no matter what x value you choose, like let's say this is the value a, as x approaches to a from either direction, you choose little x values there and little x values there, and you get closer and closer and closer to a from either direction. From either direction, the outputs are just going to be these little values in here. Right? The outputs are going to be these values out here. So no matter what you choose, the output is always going to be the 8. This guy. Good. So the limit as x approaches to a of the function f of x equals to 8, right? In this little example. Okay. But f of x is 8, right? So I can also write it as, or I can write it as the limit as x approaches to a of 8 equals 8. And there's nothing special about the constant 8. It could have been any constant. And that's where this property comes, right? So for this one, you can also think of it as some function f of x that equals the constant c. And so the limit as x approaches to a of that function is just going to be equal to that constant. Good. All right, the next couple, these two are really, really important for a vast majority of the work that you do in calculus. So this is saying that if we have a very simple linear equation, y equals to x, then the limit as x approaches to a of f of the function is equal to a. Right? It's another straightforward one. So if we have f of x equals to x, then when we graph that guy, it's going to be a very simple linear equation. It goes through the origin like that, right? It's got slope 1, slope equals 1, and 0, 0 is the y-intercept. Right? This is that function. So this second property is indicating for us that if we have some constant here, say a, right? If we have f of a, the output is also going to be a. Right? And that's true for any one of these numbers. So it could be a 1 equals 1 and 7 equals to 7. That's what happens if you want to write it in this notation, y equals to x notation. It means that every point on here, an ordered pair, is an ordered pair where the x equals to its y. Good. This is going to be the ordered pair a comma a in here. Good. So now as x approaches a from either direction, right, as we choose little x sub 1 there, and an x sub 2 there, and an x sub 3 there, or an x sub 4 there, and an x sub 5 there, and we get closer and closer and closer, closer and closer to a from either direction, the outputs are going to be values on our graph are going to be values that are here and here and here and here and here and here, and they're going to get closer and closer and closer and closer to the value a. So I can write that the limit as x approaches, the limit as x approaches to a from either direction of my function f of x is going to be equal to a, right? Just looking at this. But then f of x is equal to the x function. So I can write it down as the limit as x approaches to a of x equals to a, right? And that's what this is. Any questions about these two so far? No? 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 Okay, and then this third one is really important. It's indicating that if we have n as a positive integer, so n equals to 1 or 2 or 3 or 4, dot, 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 right? So if we have cases where we have x to the power of 1, x to the power of 2, x to the power of 3, so on and so forth, any one of those positive integers, then the limit of, as x approaches to a, of that x to the power of n is equal to a to the power of n. Right? That's really, really important. This, we can kind of couple our prior rules. We had a rule that said this: the limit as x approaches to a of x to the nth power, right? Well, we already had a rule that indicated that what we could do is first find the limit and then raise it to the power of n, right? We've already exercised that rule. And so now the limit as x approaches to a of x, well, we just saw that that must be equal to a. So this must be equal to a to the nth power. Right? So this one leads to that one. Good. So this property, along with the addition and subtraction properties 1 and 2 of the previous box, allow us to deal with polynomials. Good. Okay, so this one is similar in that it's allowing us to change the order of operations here, just like we did before. We can bring the limit on the inside, say, and the limit as x approaches to a of x is equal to a, so this is just going to be equal to the nth root of a. All right, let's see how we can apply those to these. So, for example, let's say that we want to find the limit as x approaches to 5 of this polynomial here. Okay, so our first addition and subtraction properties of the rules of limits, the laws of limits, allow us to separate it into the summation and the difference of each one of these separately. So the limit of this entire thing, so it's a subtle distinction, right? So be careful with calculus 1. All these tiny little distinctions can be a bunch of points that get deducted. So this is the limit of the whole thing is equal to the limit of the first one minus the limit of the middle one plus the limit of the last one. Good. Okay, and now we have some other properties we can use. We can bring out constants. We have that property. This constant and this constant can be brought out. That's where we have this 2 here and then this 3 out here. Good. And then we were just now given that if we have x to the power of 2, this is equal to the limit as x approaches to 5 of x, and then in parentheses, squared. Good. So maybe I would have inserted one more step here if I was doing this. Let's paste this thing in. Right, there's maybe like one more step that can go in here. This is the equal to 2. And then in brackets, it's the limit as x approaches 5 of just x, and then squared. Good. And then everything else stays the same. And the limit as x approaches to 5 of x is going to be 5. Good. The limit as x approaches to 5 of x equals 5. Okay. Any questions? No? Same thing for b. We have one giant fraction. The limit of this giant fraction, well, we have one property that says that we can separate this into the limit of the numerator, the limit of the denominator, find them separately, and then divide them. Okay, so the limit of this giant fraction, right? We start off with the limit of this giant fraction. Well, we know we can find the limit of the numerator and the limit of the denominator, and as long as that's not 0, this is valid. So we just have to make sure we're not going to accidentally get a 0 down here. Okay, so now we can separate these into a bunch of different steps here. So the addition and subtraction laws of limits, law 1 and law 2, tell us that we can separate this into the addition of the first one plus the addition of the middle limit minus the subtraction of this last one. Right? We can pull out constants. And as like I said, one more time, I could also find the limit of this by just finding the limit of x and then the whole thing being raised to the power of 3. Okay. So we're just using our limits and we end up with the answer we needed. Any questions on these? No. Okay, so by these two examples, we can conclude this, and again, it's not really proven, but we can reasonably conclude that if f is a polynomial or a rational function, and a is in the domain of the function, then the limit as x approaches to a of f of x is equal to f of a. This is what people often think is true about all functions, but this is saying that's actually only true, or we're only allowed to assume that it's true, for polynomial and rational functions. When you're given either a polynomial and rational function, you're asked to find the limit, then as long as the a is in the domain of the function, then you can just plug it in and find the answer. Does that make sense? So for example, if I give you some polynomial function, f of x equals to any crazy weird thing, x to the 4th power minus 3x cubed plus 2x squared minus 9. This is a polynomial, right? So if I want to find the limit as x approaches to 1 of f of x, then technically we could go through all the rules to separate into addition of the limit as x goes to 4 minus 3 times the limit as x goes x cubed, and so on and so forth. But this tells me that I could just evaluate the function at 1 and we'll get the same answer. Good? Questions? Okay. The reason this is true is because the function functions with this direct substitution property are called continuous functions. Continuous at that point at least. So a polynomial function is always continuous for any value, but a rational function might not be continuous everywhere. There might be problems, right? There might be an asymptote that shoots off to positive or negative infinity. Or there might be a little hole, right? Someplace where it's just undefined. So rational functions might not be continuous everywhere, but in the places where this is true, where the value is in its domain, then it's continuous at that point. Did that make sense? Okay. So all of this is justifying that if you're given either one of these to find the limit as x approaches to 3, then all we have to do is plug in a 3 here. That's what the answer is going to be. Good. So here, let me write some stuff down. For a, we have the limit as x approaches to 3 of 2x cubed minus 10x minus 8. Okay, so if we were just following the prior laws of limits, we would then say that this is equal to the limit as x approaches to 3 of 2x cubed minus the limit as x approaches to 3 of 10x minus the limit as x approaches to 3 of 8. Then we can pull out that constant and say that this is 2 times the limit as x approaches to 3 of x cubed minus the limit, minus 10 times the limit as x approaches to 3 of x minus the limit as x approaches to 3 of 8. And this would be 2 times 3 to the power of 3 minus 10 times 3 minus 8. So this would be 2 times 27 is 54 minus 30 minus 8. So this is equal to 16. Okay, so here we're using the laws. Using limit laws. This is how we would find the answer. However, this other property here, limits by direct substitution, this guy is telling us we can avoid all this work. Why do all that work when we can just plug it in, right? This is saying that this is equal to the function evaluated at 3. So I can just plug in 2, plug in a 3 cubed minus 10 times 3 minus 8, which ends up being like this step over here, except we got to that step by on this right-hand side by following the laws of limits, or the limit laws, whereas here I'm just doing direct substitution. Good. Okay, same thing here. I could use the laws of limits to separate this and find them all that way. Or this direct substitution tells me that I'm allowed to do this, -1 squared plus 5 times -1 all over -1 to the power of 4 plus 2. Good. It's going to be 16. And this guy is +1 minus 5 divided by +1 plus 2. So it's going to be -4/3. Any questions? 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 Okay, back to this guy. We saw this before. How do we figure this out? Well, we can start plugging in numbers in one direction or the other. Or what we could do is factor and then realize that in this case we're allowed to cancel. So note that the limit as x approaches to 1 of x minus 1 over x squared minus 1 is equal to the limit as x approaches to 1 of x minus 1 divided by x minus 1 over x plus 1. Okay, so note that if x equal to 1, then x minus 1 would be equal to 0, and so x minus 1 over x minus 1 times x plus 1, we'd have an undefined denominator, right? We'd have a divide by 0, so the whole thing would be undefined. Is that okay? So we start off with this. We can factor the denominator. We get these guys. This guy in here. Okay, now if, this is a big if x was exactly equal to 1, then 1 minus 1 is 0, and then we'd have an undefined. Luckily for us, this right here means that x gets close to 1, but never equal to 1. So we're not interested in 1. So this doesn't apply to us, right? For us, oops, let's not do that. Come on, erase. But the limit as x approaches to 1 means x is never equal to 1. Only very close to 1. It means x is values close, I'll put that in parentheses, close to 1. Never actually equal to 1, right? We're specifically forbidden from considering what happens when it actually equals to 1. So we are not allowing x equal to 1, thus x minus 1 is never equal to 0. Right? Because x is never equal to 1. It's something close to 1. It might be close to 0. Right? X minus 1 is close to 0. Never actually 0. But never 0. Is that okay? So therefore, this is not a dividing by 0 situation. My whole point to this whole thing is that as long as we're only considering the limit as x approaches to 1, this is not a 0. Therefore, I don't have a dividing by 0. Therefore, I'm allowed to cancel them. This is just some small decimal, right? Maybe it's 0.01 or something, 0.001, it doesn't matter. Some small decimal in the denominator and the equivalent number in the numerator. Therefore, they cancel. Good. And so since they cancel, they reduce to having 1 over x plus 1. And now you can just apply our prior rules to solve it and plug in the 1. Okay. The numerator and the denominator have a common factor of x minus 1. When we take the limit as x approaches 1, we have that x is never actually equal to 1. Therefore, x minus 1 is never equal to 0. Therefore, we're allowed to cancel these. Right? So the limit as x approaches to 1 of x minus 1 over x squared minus 1 can be reduced to the limit as x approaches to 1 of 1 over 1. And now, using our other properties of limits that we've been looking at, 1 is now in the domain of this rational function. So we can just plug it in, and we get an answer of a half. And that matches with what we thought it was before, when we used our calculator and we're just plugging in numbers and getting closer and closer and closer to 0.5. Now we have a more algebraic reasoning for concluding that that's the valid answer. Okay, good. Questions, 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 questions? So the moral of this example is that if you're given something like this, first of all, if it's a polynomial or a rational function, we know that it's a really simple limit question, that the answer is going to be very simple if you can just plug it in and get a valid answer. Right? As long as this is in the domain, we can just plug it in and get an answer. Unfortunately, in this case, it's not in the domain because we end up with a 0 over a 0 situation. So I know that 1 is not in the domain of this rational function, so I can't just plug it in. Okay, luckily though, I can factor and cancel. And I'm allowed to do that because under this consideration, the limit approaches 1, we know for a fact that I'm never going to consider the actual case of x equals to 1. Good. So for that reason, I can cancel them because this is not a 0 over a 0 situation at that point. And I end up with something that's a little more simple to work with. This is a rational function where 1 is in the domain, so I can just plug it in and get our answer. Good. Okay, left-hand limit, right-hand limits. Okay, so the limit as x approaches to a of f of x equals to L, if and only if it's true that the limit as x approaches to a of f of x from the left-hand side equals to L, and at the same time, the limit as x approaches to a from the right-hand side of f of x also equals to L. Right? So this is an if and only if, meaning that if you know one side, it automatically... What the hell is happening here? Stop it. Means that if you know one side, it automatically means that the other side is true. So if we know that that's true, it can lead us to conclude that that must be true. Or the other way around, which is often the case. We usually work with this, where we can show that the limit from one direction equals to L, the limit from the other direction equals to L, therefore we can conclude this. Here's an example of where we might need that. the limit as x approaches to 0 of the absolute value of x show that it equals to 0. Okay, so notice that that description, the definition of the absolute value of x is can be written this way. It equals to x if x is positive, and it equals to negative x if x is negative. Right? If we graph this thing, it'll look like this. It looks like a V. Right? This is what the graph of absolute value of x looks like, where this is the x function and this is the y function. So this part here is kind of like the line, right? If I thought about the line going this way that went on forever, it's a little like the line y equals to x, but it's restricted to only be for positive values. And then if I go this way and think about this thing over here, it's kind of like the line y equals to negative x. Good. It only goes in this direction. It's got a -1 slope going through the origin. So we can break this absolute value function into these two cases, and now we can consider them separately. So the limit as x approaches to 0 from the right-hand side, so if we're approaching this way, x is approaching to 0 from this direction, then the outputs are heading towards 0. And if we approach x goes to 0 from the left-hand side, then the output values are also approaching 0. So the left-hand limit and the right-hand limit both approach 0. Therefore, we can conclude that the limit of this equals 0. The limit as x approaches to 0 of the absolute value of x that in fact does equal to 0. Good. Questions, 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 questions? Right? And there's the graph for it. Better graph than me. Come on. Any questions, any questions, any questions? Let's take a quick look at the examples in your book and see if we're ready and prepared and armed to answer all of these things. Okay, so we have the properties, the limits, the boxes, okay. Okay, so these are the examples from your homework. So sometimes you'll be given a graph, and from the graph you'll be able to figure out the limits that they're asking you for. So the limit as x approaches to 1 of f of x, for example. X approaches 1, and then this one's f of x, and this one is g of x. So looks like it's 1, right? The limit as x approaches 1 of f of x is 1. Okay, and so we can use the different laws of limits to be able to figure these out. We did examples like those, so those should be good, I think. Okay, so again, here they're giving you the value of the limit. So instead of giving you a graph, they might just give it to you. The limit as x approaches to a of f of x equals to -3. And then this limit and this limit. And so you can use those combinations to be able to figure out these guys. Right? Again, using the laws of limits. Easy stuff. Okay, these guys get a little bit more complicated now. Say, for example, these. So remember that our substitution rule says that if you are given a polynomial or a rational function, then we're allowed to just plug it in as long as that value that you're plugging in is in the domain of the function. So we'd have to kind of test it out first and see what it is. So for example, number 9, just a polynomial. 4 is in the domain of the polynomial, so we could just plug it in, right? If they allow us to. Now it might, you know, on your exam, for example, it might specifically say use the limit laws or the expanded limit laws, whatever they're called. Supplemental limit laws, what are they called? Additional limit laws? Limit laws. So there's the limit laws, and then there was some special limits. Okay, so the limit laws, special limits, and then limits by direct substitution. evaluate if they exist. And it says using limit laws. Okay, so see, for examples 5 through 18, they want you to use those steps, breaking it down so that we know that this equals to, say, number 9. This equals into finding the limit of the first term minus the limit of the middle term plus the limit of the last term. Then we're allowed to move out a constant, right? So we have various rules we're allowed to use. 19 through 32 doesn't restrict you on what you can do, so you can do whatever you want. So if you're given a rational function, say like number 19, we know that if this 2 is in the domain of the function, then we just plug it in and that'll be our answer. Same with, say, like number 20. If we just plug in a -4 and then -4 is in the domain, then that'll just be our answer. If it's not in the domain, then what we could do is try and factor, reduce, cancel, get to a point where 2 is in the domain of the resulting rational function, and then we can evaluate it. Good. If none of those things work, then we can just go back to our calculator and try different values, right? Try the table method. Plug it into your calculator, look at a table, and plug in different values until you're convinced that either the limit exists or it doesn't exist. Okay. Good. Okay. So try out this stuff and let me know if you have questions tomorrow. I think this is a good place to stop for now. Okay. Any questions on anything? No? Okay then. I'll see you tomorrow then.